Welcome to the fourth part of this lecture on bevel gears and worm gears in the course Advanced Machine Elements at Luleå University of Technology. The fourth part is now about worm gears. And a worm gear has crossing axes. The axes are also non-parallel and non-coplanar. They offer a great advantage of very high gear ratios. You can get ratios from 1 to 1, even up to 300 to 1, without too big gears. They also offer the possibility of self-locking. I will be discussing this later on in the next part of the lecture. And the worm gear consists of two gears. You have the worm, which is shown right here, the silver or steel color part here. It has a small diameter and very few teeth. The number of teeth is typically between 1 and 3, and it has a relatively large helical angle. The worm gear, which is the large one over here, has a large diameter and a large number of teeth, and this combination offers you high gear ratios. In worm gears, you also have a high amount of sliding due to the configuration of the gear, basically. This obviously gives you lower efficiency. The losses in a worm gear is in the range of 10%, maybe even more. Now, the high amount of sliding results in heat generation due to the friction generated between the two gear teeth that are sliding against each other. This requires adequate cooling when you design, for instance, your housing for the worm gear. You also encounter high wear rates in these systems due to the high amount of sliding. And a typical way of solving this is that you make the worm from steel and the worm gear from, for instance, bronze. One of the reasons is that it's easier to replace the worm gear, so you basically sacrifice one of the parts of the gear system. Typical applications where you may find worm gears are winch drives, like the one shown right here. The worm gear is positioned on the side here, and then you have your winch system right here. One of the benefits here would be that you have the self-locking ability of the gear, and it also offers high gear ratios. You can have a smaller motor, for instance, driving the winch. And for those of you who have been or are playing guitar, or at least try to tune a guitar at some point, you have been using a worm gear. The tuning screw on a guitar, this is the knob that you're turning, and the guitar string is wound up around this axis right here, and you have a worm gear down here, which gives you high gear ratio, and it's self-locking, so the string will stay under tension when you release the knob. Typically you found three variants of worm gears. You have the cylindrical worm, as shown right here, and a globoid worm gear, where you have this shape of the worm gear. You may also have the opposite, with a globoid worm and a cylindrical worm gear, as shown there. Or you will have a globoid shape on both the worm and the worm gear. So these are the three variants that you would commonly encounter. Moving on to the geometry, the worm, now so if we start with the worm, this one is defined by using the pitch diameter, which is D1, shown right here. Z is the number of teeth, so in this case you see L right here equals pi times the module, and this would mean that you have one gear tooth in this one. In this case, L would be this distance over here, meaning that you have two gear teeth. So that's the way you distinguish between different number of teeth, and as I said, the most common is between 1 and 3. You have the pressure angle, you have a helical angle, and you have a third angle, gamma here, which is 90 minus beta 1, or the helical angle. If we look at the worm gear, we also have a pitch diameter. We have Z, number of teeth, obviously. The module, the normal module, Mn. The pressure angle, we have the helical angle, and we also, not necessarily, but we may have a correction factor x2. Now, since the worm is in essence a rack, like a rack and pinion type system, so where the correction factor doesn't play any role, there is not a correction factor x1 defined for the worm. There's only one x2 defined for the worm gear. When it comes to meshing of these gears, these are the 4 conditions that need to be met for meshing to occur in a correct way. You have to have the sum of beta 1 and beta 2 equal to S here. We have the shaft distance A, which needs to be d1 plus dw1 over 2. These can be rewritten as d1 plus d2 plus 2 times the correction factor times the module. The pressure angle has to be the same in both cases, and you have to have equal normal pitch or diameter or module also, Mn and Mn2. The gear ratio then, the speed on the pitch diameter would be equal for both gears, obviously, since they are meshing and interacting with each other. You will have the same speed on the pitch diameter. So Vn1 would be equal to Vn2. And then we base our calculations on the pitch diameter, and for helical gears you can find the expression dw2 or dw1 equals to d2 over d1. So we can then use the pitch diameter for these calculations. So these 2 figures, they show the velocities and the different angles of the worm gear and the worm. So for Vn2, which you have right here, that would be equal to Vn1, which you have down here for the worm. Vn2 can be expressed this way, d2 over 2 times omega 2 times sine beta 2, which we have based on the geometrical relations here in the figure. In the same way, we can write Vn1 as d1 over 2 omega 1 sinus for gamma 1, which is this angle right here, and beta 2 is the angle up here. If we set beta 2 equal to gamma 1, we will end up with an expression where we have the ratio between omega 1 and omega 2 equals to d2 over d1, 1 over tan for the for gamma 1. But we need to calculate the pitch diameters to get something useful out of this. So we calculate the pitch diameter this way. For the worm, we start with a pitch, pt, which is the normal pitch divided by sine over gamma 1, and we have the circumference, pi d1 equal to pt, which is the pitch again, and z1. If we solve this for d1, you will end up with an expression that you see here to the right, where you have the module, number of teeth, and sinus for gamma 1. According to the same procedure, we have the pitch for the worm gear. In this case, we have cosine beta 2, and we have the normal pitch. We have the circumference, pi d2 equals to pt times z2. Again, solving this for d2 gives us the expression mnz2 over cosine for gamma 1. And if we then take all this and we put it back into the equation that we had on the previous slide, we will end up with the ratio between the angular velocities, omega 1 and omega 2. And then we put in these expressions that we have just derived, and out comes z2 over z1. So what does this tell us? Well, it tells us that the gear ratio for a worm gear, despite its slightly different configuration, is given by the ratio between the number of gear teeth, in the same way as it is for cylindrical gears. So I thank you for your attention listening to this fourth part, and I hope you will enjoy the next part of this lecture.